Why, hello there. Today we're going to be discussing a write-in question. Now, the write-in question happens to be in front of you. There are lots of write-in questions, so you might be thinking about which one. It's this question right here, 25.4. And this write-in question happens to be from our textbook, that is University Physics, Young and Freeman's 13th edition. Now, this is in Chapter 25, Discussion Question 4, as you can see. Take a minute to read it, and then we're going to get right to answering the question. All right, so here I am, Mr. Rose, working on question 25.4, write-in question 25.4, and hopefully you've read it already, but the abridged version of the question is, we have a wire. Well, we have two wires. One thick wire, that's represented by this big coffee cup, and one smaller diameter wire represented by this marker. And what happens if those are connected and there's electricity? There's current flowing from left to right across your TV or cell phone or computer screen. What happens if there is current traveling from the thick wire into the skinny wire? We're going to discuss really what happens to that, what happens to the amount of current, what happens to the force, or what force is responsible for that, and or the drift velocity, or the speed of the actual electricity. So the first thing we want to know is if these things are hooked up like so, and this would be kind of an example of part of a series circuit. In other words, all of the electricity is going from here to here. So current, or those charge carriers, that's represented by I. I'll put that up on the board here. I is our current. And that is the actual electricity flow. That's not going to change. So the amount of current, or the amount of electricity going from the fat wire to the skinny wire, has to be the same amount. So the current value, we can call it 5 amps. 5 amps is never going to change. Well, what about the actual velocity of the current? That's what we call drift velocity. Remember, electrons are not actually traveling in a line. They are drifting in kind of chunks all the way down. We're taking call it the average, or that drift velocity. Well, if we remember the drift velocity equation, that drift velocity, VD I'll call it, is the current divided by the charge of an electron, or our charge carriers, the number of charge carriers we have, and the cross-sectional area. So that's N, that's an E, and that's an A, where N is the number of charge carriers, E is the actual charge, 1.6 times 10 to the negative 19th, and A is the area, the cross-sectional area. So if I just look at this overall value, right, if my cross-sectional area goes down, so this number gets smaller fractionally, current staying the same, my drift velocity is going to get faster. So as the current stays the same going from my big wire to my small wire, the current remains constant, but the drift velocity, VD, has to increase. Much like you could think of it as water. We always talk about water going through a hose. If you put your thumb over the end of the hose, the same amount of water comes out, but now it's going at much higher pressure. So that drift velocity is going to increase. The question also asks about force. What is the force that's making this happen? That has to be the electrostatic force, or just the no, I like the electrostatic force, F. And what's going to happen with that? Well, theoretically, if the drift velocity is increasing, then the force that's moving it through is also going to increase. So technically, that force would increase in the smaller diameter wire. Well, I hope that answers your write-in question. Keep these questions coming. It's really nice that you have them all typed up into the textbook, so I'm here to answer them. But that's all I have for you. By all means, feel free to like, click, or subscribe to the YouTube channel, or just bring some questions and we'll shoot answers out to you. That's it, you guys, and you'll see me next time.